Alright, this is the last problem in the bearing setup. And this is a very practical sort of problem. We actually mentioned something along these lines in class today, Tuesday, which is that if you have an average electric motor sitting with the shaft horizontally, there's typically going to be no axial force on the bearings. But as soon as you turn it upright, so that the shaft is upright, the mass of the armature, the mass of any pulley, the mass of the shaft itself, all of that is going to act downward onto one or both of the bearings. I'm making the assumption here that all of the weight is reacted through the bottom bearing. If you look back at the general notes on shafting, it's usually preferable to react axial loads through a single bearing. So in a case like this, by having a loose sort of fit on the inner race at the top, that would simply allow the bearing or the full weight to drop onto the lower bearing at B. If it was a tight fit on bearing A and a loose fit on bearing B, then bearing A would take it all. And without knowing how the motor is manufactured, you just kind of have to make an assumption, which is what I'm doing here. I've already gone through the free body for this. We've got 150 pounds of belt tension at the top. Then we have reaction loads at bearings A and B. And you can see, since all of the weight is going to the bottom bearing, it's the only one with a Y component, 95 pounds. Bearing A has a much higher radial load than bearing B, several times higher. However, the effect of that axial load could easily be enough to make bearing B the more critical case, which in this case would be to say that the life of bearing B could be lower than bearing A because of that axial load. Also, my dog is chewing a bone behind me, so if you hear weird noises, that is most likely what it is. Alright, so essentially we have to carry out analysis on both of these bearings, and we're going to start with the top one just because it's we know how to do that analysis. We've already gone through it. So that bearing designation in the problem statement 203, the 200 means that it's a single row light bearing. The 03 specifies the bore diameter as 17 millimeters. You can actually get that information from the single bearing specification page pulled from the Timken manual, which is attached to your notes. The C10 value for that bearing is 9.56 kilonewtons. And I'm going to convert that to pounds since all my other forces are in pounds. So that's the problem setup. Pulled all the information. We can calculate the life of the top bearing now. And since I'm taking this to be at 90%, I'm just using the straight catalog load. If I'm doing the same problem with a different reliability specified, I would just have to use the Weibull equation to calculate the life. That's it. We did that in a previous problem. But since we have 90% reliability, we can go straight to a form that says the design life is equal to the rated life times C10 over FD raised to A, which we have 10 to the 6, 2150, 171.4, and since this is a ball bearing, A is going to be 3. That gives me 1.974 e to the 9th cycles, which at our rotational speed is a life in hours equal to 34,810. So a reasonably long life on that one. Now the question is that the bearing that's going to fail first, or is the bottom bearing going to fail first? The work on the bottom bearing is a little more involved, a little more complicated, but there are a few more steps to this. Alright, so for an analysis where you have an axial load and a radial load, you are dealing with both forces in the calculations. So I'm going to go ahead and specify them. The axial load is my 95 pounds, and the radial load is 21.4 pounds. V, that is a dimensionless parameter that basically specifies whether the inner race or the outer race is rotating. In our case, the inner race is rotating, and the correct value for that is 1. So there we go. Now the C10 value for this is the same as before, 2150 pound. We also need the C0, that is the static load rating for this bearing. From the same table, it's 4.5 kilonewtons or 1,012 pounds. And that general relationship there, you can see C10, the dynamic rating, is about twice the static rating. That's pretty typical for the light-duty ball bearings, at least, that the dynamic rating is in the ballpark of twice the static rating. Now, the very first thing we do, and all this is based on table 11-1. First thing we do is calculate the axial load, FA, divided by that static load rating, C0. So we have 95 divided by 1,012, or 0.094. Now from the table itself, we now need to interpolate the lowercase e, the abisca. And so I'm going to take the range, I'm not going to actually sit here and interpolate, but you guys know how to carry that sort of thing out. And I get about 0.288 as my E value when I do so. The next thing to calculate in the process is FA over VFR. All known values, once again, FA is 95, V is just 1, and FR is 21.4. That's 4.44. That is definitely, without a doubt, greater than E, which is 0.288. What that tells us, and this is all right in the table itself, is that we need to use the X2 and Y2 parameters. So X2 is a constant of 0.56. Y2 we are again interpolating. And doing so, we get about 1.512 is equal to Y2. Now with X2 and Y2 and V, we can calculate the equivalent radial load FE. That's X2 times V times FR plus Y2 times FA. So I have 0.56 times 1 times 21.4 plus 1.512 times 95. And we get FE equal to 155.6 pounds. Now we can go ahead and tell that FE is now effectively FD in calculating life. And FD in the top bearing was 171.4. So FD in the bottom bearing, the equivalent is 155.6. Without going further, I can say that the top bearing is going to fail first. It's got a higher load, it's going to fail first. But just to show that there's no different in the process, we'll carry this out. LD for the bottom bearing is going to be LR times the C10 value divided by FD. The entire term raised to the A, which is 3. And LD is now 46,530 hours. So that top bearing, without a doubt, has the shorter life. It's not going to let me erase that, but 46,530. The top bearing has a shorter life. It would be expected to fail first. Knowing that, you can put some maintenance plans into place, and you kind of have a sense of what's required down the line. What are you doing, thing? Stop. If I don't learn how to edit video, you'll get to see all this. It's not very interesting. I'm emphatically telling it to stop, and it's not stopping. I think I may have filled my RAM up. Now, do not close. No, no. It's like it's no longer going to take mouse commands. How about pause? We can pause it. Nope. Oh, man. This is infuriating. So, nothing works. Mac is still free, as can be. The virtual PC, dead to the world. It's still going though, which gives me some hope.